Good morning and welcome to my crazy hair day. Today we're going to discuss chapter 1.5, and this is really important because the questions in chapter 1.5 don't really fit what is described as pieces of the curriculum in unit 1.5. So, first of all, take a look at this. Most of you know that the atom is made of the nucleus, which is made of protons and neutrons. Protons are positive and neutrons are neutral, and each proton carries a charge of plus one. And then electrons, which are moving around the nucleus, which each carry a charge of minus one, they don't move in a circle, but it's just advantageous for now to represent it like that. So you can also see some terminology related stuff here, such as the energy level, which is the most far away from the nucleus, is called the last energy level or the outer shell, while the energy level closest to the nucleus is called the inner shell or the first energy level. You will see why this is important later. Now, Coulomb's law defines the attraction between charged particles. See, in the atom, the reason why the electrons cannot just run away, because electrons have a lot of speed, a lot of velocity, but they cannot run away because they're attracted by the plus. And the size, the strength of this attraction is defined by Coulomb's law. So you can see Coulomb's force equals Q1 times Q2. Q1 and Q2 is just the number of charges. So, for example, Q for this nucleus will be plus 3 because it has 3 charges, right? And for this electron will be plus minus 1, right? And then you've got r squared, which is the distance between particles. So you see Coulomb's force is much stronger between this nucleus and this first electron than it is between this nucleus and this last electron, right? You also remember that plus and minus attract, right? While two minuses repel and two pluses repel. Now, why is this important? Because take a look at this. You've got lithium and beryllium here. The main difference between them for our consideration now is that beryllium has four protons, while lithium has only three. What does that mean? Coulomb's forces between this nucleus and each of these electrons, because that's four different Coulomb's forces. These Coulomb forces are much stronger than the forces between lithium's nucleus and its own electrons. What does that mean? That we say that beryllium has a larger effective nuclear charge. Effective nuclear charge depends on number of pluses and size. For us now, the size is not important. That's going to come later. So now, effectively, whatever has a high number of pluses has a higher effective nuclear charge. And that means that the electrons in beryllium are closer to the nucleus because they get more attracted by this plus. It also means that it's easier to remove the electron from the last energy level of lithium than it is from the last energy level of beryllium. Because see, they're kind of the same distance. I mean, yeah, this one is closer, right? This one is more far away, but more importantly, this one is attracted by four pluses, so it's much more connected to the nucleus. So it's much easier to remove the electron from lithium from the last energy level than it is from beryllium. And we say that this means that lithium has lower ionization energy because ionization energy is the energy you need to remove the electron from the last energy level. So if it's more difficult to remove it, that's higher ionization energy. And that would be beryllium. If it's easy to remove it, that's lithium, lower ionization energy. We will talk about this more in the next few videos. Now, take a look at this. This is also in some of the questions. So, electron configuration. I beg you to please memorize this. Because if you memorize this, you'll be able to solve most of the questions that ask about the electron configuration. What is this? This is just the order in which the electrons are put in energy levels and sublevels. Again, we will discuss this later. So, this is the first energy level, 1s, first energy level, first sublevel. And it can fit two electrons, which is represented here by this two. And it got second energy level, first sublevel with two electrons. And it got second energy level, second sublevel, six electrons, and so on and so forth. So please memorize this. Important to remember also that the S sublevel can only fit two, while the P sublevel can fit six. And again, you have here some terminology related stuff. So this is called a half full orbital. I'm just reminding you because this was in the Moodle course already. And this is called a full orbital. So if the line fits two electrons, that's a full orbital. If the line fits one electron, that's a half full orbital. If we got an empty orbital with nothing in there, that's just called empty orbital, right? Uh, Last energy level is this one, right? You look at the number here. That's three, the highest number. That's the last energy level or outer shell. Also, in some of the questions, they have this. So the so-called excited state. Take a look at this. This is just a normal electron configuration of sodium, right? So you got 11 electrons, and what you want to do is fill this out until you reach number 11, right? So 1s2, that's 2 electrons, 2s2, that's another 2, and then 2p6, that's 10, right? And then 3s1, that's 11 electrons, and this is an electron configuration of an atom called sodium, Na, right? But that's its ground state. Ground state is the natural state of the lowest energy. However, there is another state which is called the excited state. What does it mean? Well, see, this looks weird because if you're filling this in order, it should look like this. It should be 3s1, but this is 3p1. This means that the last electron in the last energy level just went higher. It went to another sublevel. It's not doesn't look like a normal state. This means it got energy from somewhere and it went up. But this is an excited state, which is unstable. I mean, excited, not stable. So what this configuration will do is this electron will return to a lower level or a lower sublevel, and it will emit light. This is something connected to a lot of phenomena uh, when light is made. For example, your light bulbs work basically like this. So the electron goes up, but that's not stable because everything in nature wants to have minimum energy. Then it goes down, and that energy difference is emitted as light or a quantum. Sometimes I'll say quantum. Okay, so now let's just do some questions, some examples. So, how many ampere electrons does S have? What do you want to do here? Well, you want to just draw the electron configuration. See, the unpaired electrons only happen in the last energy level because you're filling the electron configuration from the bottom up. So when you get to the last energy level, that's the only place where you might have some orbitals which are not full. So I only care about this basically. I don't care about this because I know this is full, right? Because it fits basically this, right? But the last one doesn't. So I just draw it and I can see I've got two unpaired electrons or two half-filled orbitals. So this is this unpaired electrons. Take a look at this. Which electron configuration will emit light quantum of energy? So this is what I'm talking about. Now we need to find something that doesn't fit the proper electron configuration sequence. So which one is it? This is good. This is good. This is not good. So it should be 2s2, right? Can be 2s1, 2p1. So this is an excited electron, right? So we've got our answer. Yep, it's correct. Now, what is the electron configuration of Ca2 plus and Cl minus? So you can see how I did this. Basically, if they ask you for an electron configuration of anything, you just need to go to the periodic table and find the number of protons which then equals the number of electrons, right? However, this is Ca2 plus, which means this atom here has two less electrons than it should have. So normal calcium and neutral calcium has 20 protons and 20 electrons. But this is Ca2 plus. That means two electrons have gone away. So you need to fill the proper sequence of electron configuration until you get to 18, not 20. And then you just get 2 and 2, 4, 6, 12, and that's 18. Good. This is another example with ions. So this is Cl minus. So now you've got one extra electron. So again, the atomic number tells you the number of protons. So you know this got 17 protons. But this is the electron configuration. This is where you put electrons. So this will have 18 electrons because another electron just came in, right? So electrons can come and go, but protons can't. So basically, you fill this until you get to 18, and you can see it's actually the same like this. It's exactly the same. Uh, which electron configuration represents an atom with the lowest ionization energy? Now, the thing is, if you remember the Coulomb's law, you remember that there is under on the right side of the equal sign down, you got r squared. That means if something has more energy levels, in that last energy level, the electrons are way too far from the nucleus and very easy to remove. So if I take a look at these, I will see that this is the only atom which has three energy levels. So this electron, this last electron, is just very far from the nucleus. So that's the first thing you look for when you talk about ionization energy. First, you look at what has the highest number of energy levels. But if you've got something like this, where you got equal number of energy levels, this is second energy level, this is also second energy level. What will have the lower ionization energy? This or this? It's going to be this, because the nucleus of this only has 3 protons, assuming it's a neutral atom, while the nucleus of this will have 10 protons, so much higher Coulomb forces. But definitely this will have the lowest ionization energy because this last electron is the energy level 3, so it's very far. Wait, try to do a bunch of these. Let me just recheck if I'm correct. Yeah. So practice these and let me know. Bye bye.